Hello everyone, and welcome to this video on section 5.6 called Ratio and Root Tests. In this video, I'll be taking you through a preview version of a Newton Alta assignment for section 5.6 on ratio and root tests. Please understand that the questions I see in this video may not be the same questions that you see when you work on the assignment yourself. But the objectives are the same, so hopefully the questions are similar enough. Watching me do them here will help you out when you work on it on your own. All right, so here's what our Newton Alta assignment page looks like. At the title of the section in the upper left corner, you won't have the word preview. Upper right corner, you got your mastery bar, right, telling you how far along you've gotten. Then you have the activity log next to that. It shows you how far along you've gotten with each objective. Looks like there are 3 individual objectives here. And on the main page, you have a current objective. And below that, pardon me, I had a call there. You have a question related to that objective. And then beneath each question, you should be seeing a feedback button. Right, if you see any issues with the question, typographical errors, problems with the answers, whatever, you can send in some feedback directly to Newton, and hopefully they'll look at it and get back to you and have a fix for you. Next to that, you will not see this instructor cheat button, right? This is for instructors only. But you will see a more instruction button. So if you're ever struggling with an objective or a topic, click on this. You'll be taken to a page with some reading to do or videos to watch or both. And then you'll be given some questions related to that instruction. And you can work through the entire assignment this way. Anytime the more instruction button comes up, you can click on it, go to the instruction page, and work on the assignment problems with the instruction available. And there's absolutely nothing wrong with that. All right. So the first objective I'm seeing is determine the appropriate convergence test for a series. All right, so we've seen throughout the chapter 5 sections lots of convergence tests. So the first one we saw was the divergence test. Remember, if the terms of your sum, if the terms you're adding up aren't approaching 0, if they don't have a limit of 0, then the series diverges. Now, if they do have a limit of 0, you can't tell right away. You got to do something else. Then you had an integral test, right? If the series of terms that you were adding up were positive and decreasing to 0, you could tell if you could integrate, do an improper integral, integrate a function that matched the sequence. And if that integral converged, so did the series. And if the integral diverged, so did the series. You had comparison tests, right? You had direct comparison and limit comparison. You had alternating series tests, right? If you had an alternating series, are the terms that are alternating going to 0 and decreasing? If so, it was convergent. And then in this section, we're going to see the ratio test and something called the root test. Well, this first question here, determine whether the series below is a geometric series, a p-series, an alternating series, or none of these. So remember, a geometric series was a series of terms where you had an exponential rule, right? You multiplied by the same number every single time to get from one term to the next. That was that common ratio. This is not geometric. P-series, you were adding up, 1 over terms that looked like 1 over n to the p. This does not look like that. An alternating series, remember, had these powers of -1 like this. See this -1 to the n plus 1 power. That's going to cause the first term to be positive, second term to be negative, third term to be positive, negative, positive, negative. This is an alternating series. And that's it. So this first question, pretty simple. Just what kind of series are we looking at? This is an alternating series. And if you don't believe it, write out the first several terms of the sum, and you'll see it's switching from positive to negative to positive to negative to positive to negative. That's what an alternating series is. All right, then after you answer a question, it's going to tell you if you got it right or wrong. Beneath it, you'll have some sort of answer explanation. Please read through these, right? Whether you got it right or wrong. If you got it right, make sure you got it right for the right reasons. You didn't just guess correctly. And who knows, maybe they'll do something in a way that you like better and will implement in future problems. Now, of course, if you got it wrong, definitely read through the answer explanations and see if you can figure out why you were wrong, where you went wrong, and try to fix those mistakes in the future. And yeah, here you see they explain what a geometric series is again, what a p-series is, what an alternating series is. So they also give you some nice instructions sometimes in these answer explanations. Okay, moving on. All right, so here we're asked to determine the appropriate convergence test for a series again. It's another one of these objective problems. Determine which of the following tests would be best to use to determine the convergence of the series below. And they give you choices. And then you have to answer this question. Does the series converge or diverge? So here's where I'll actually explain the ratio test, the root test. We have seen alternating series in section 5.5, and we've seen integral test in section 5.3. So you got 4 choices of test here, and then you also have to answer, does the series diverge or converge? All right, so first, I've already written these out. I'll explain them. So the first test in the title of this section 5.6 is the ratio test. Ratio test. So we're given some infinite series, some n equals, some starting integer, usually 1, to infinity, of the terms of some sequence, a sub n. So to apply this ratio test, find the following limit. The limit as n approaches infinity of the absolute value, because this is really a test for absolute convergence of a series. But you may recall from section 5.5 that if a series is absolutely convergent, the original series will also converge. Right? So imagine all the terms are non-negative, right? Absolute value. And then we're taking the limit of this ratio, a sub n plus 1. Right? So what does the n plus first term of the series look like? Divided by the previous one. Right? So n plus first term divided by the previous term, divided by the nth term. What happens, the limit of this ratio, terms to their previous terms, as we go further and further along the series. I'm going to call this limit L. Now, three things could happen. If this limit is less than 1, then our series, the series we were given, will be absolutely convergent, and therefore the original series we were given is convergent. If the limit is greater than 1, that would imply that terms are getting larger than the previous terms before them. So the terms, if this is the case, this limit is bigger than 1, well, then the terms of our sum wouldn't even be going to 0, and the series would diverge. And this last case is the ambiguous case, right? If L equals 1, if this limit equals 1, the test is inconclusive. Right? You can't tell. The ratio test doesn't say anything about the convergence or divergence of the series. We'd have to go and try some other test. So I'll say I would recommend the use of this test when the terms of our sequence, the terms that we're adding up, has some like factorials in it, right? The exclamation point, right? That's usually a good type of series to apply the ratio test to. I mean, you can always try it. You can always try it, but I'd recommend, when you have a sequence, when you have a series where the terms involve factorials. Just a suggestion. Now the root test. I've got that here. So again, I'll read it off, and you'll see the conclusions are very similar. In fact, the same as the ratio test. So this root test. So again, we're given an infinite series, and we're going to see what happens to, again, make these non-negative, take the absolute value of your terms, and see what happens to the following limit. Take the limit as n approaches infinity of the nth root. So the index is getting larger and larger. The root is getting bigger and bigger. The nth root of the absolute value of our terms, right? The absolute value of these a sub n's. So I'm going to call this limit L. And then we have a very similar to the ratio test, very similar conclusions. If this limit is less than 1, then our series will be absolutely convergent. And if it's absolutely convergent, right, then the original series converges, therefore convergent. If this limit is greater than 1, then the series will diverge, right? If this limit is greater than 1, that would imply that the magnitude of our terms is not going to 0. So the series would diverge. And once again, if the limit equals 1, then the test is inconclusive. Okay, you cannot tell anything about the series using this root test. Now, I would recommend the root test when our terms involve exponentials, involve things to the nth power or some multiple of n power, like the series given. I'm going to write this series that was in that problem. We have the sum from n equals 1 to infinity of the following terms. Every term looks like this: 8n squared plus 11 divided by 7n cubed plus 10. Look here, this is all raised to the nth power. So I see this exponential here, right? This nth power or some multiple of n power, something involving n as a power for the terms of our series. If I see that, I would recommend trying the root test first. Right? And I'll write up, we'll see some series later where the ratio test may be of more use. Right? Right, so these terms, right, this 8n squared plus 11 divided by 7n cubed plus 10 all to the nth power, that's the a sub n, right? Those are the terms of a sequence that I'm adding up. So if I'm going to apply this root test to this, you're taking the following limit. You take the limit as n goes to infinity of the nth root of the absolute value of our terms. Now, for n1 or greater, right, these are all going to be positive anyway. I don't see any way any of the terms will be negative. So when I write this up, we can get rid of the absolute value. I mean, I'll put it first. So this is the limit as n approaches infinity of the nth root of, the absolute value of these terms. This 8n squared plus 11 and divided by 7n cubed plus 10, to the nth power, the absolute value of all that. But again, all these, when n is larger and larger positive, these are positive numbers anyway, so I don't need the absolute value. And then additionally, when you take the nth root of something to the nth power, those like undo one another. So that's what I'm saying. Like if I see an nth power on my terms, that's probably why I'm gonna, start off using this root test. Or I recommend starting off with the root test if you're seeing some power involving n on all your terms. So this is the limit as n approaches infinity of, again, the nth root of this nth power. I'm just left with the base here, just 8n squared plus 11 over 7n cubed plus 10, and now I have a simple limit to do. The numerator is a degree 2 polynomial, the denominator is a degree 3 polynomial, and you may recall if the denominator has a larger degree than the numerator, the limit is 0. This is definitely less than 1. Right, this limit is less than 1. So by this, again, I wrote it, I'll bring it back. Remember the root test here. If I take this limit and it's less than 1, the series will converge. The series will be absolutely convergent, but therefore convergent. Right? So series converges, pardon me, by this root test. All right, so back here, the assignment, and I see this term, every term is raised to this power involving n. I'm going to say the root test would be the best test. Now you can apply the ratio test if you want. okay? It's just, it wouldn't be as pretty, I'll promise you that. It's not an alternating series. I feel like this is a decreasing sequence, but maybe eventually decreasing. So and it's positive terms. So I mean, I could try the integral test, but that would be a ridiculous integral to try to do. It really would. You have some rational function to a variable power, like I would not integral of any function like that. That's what I'm saying. So you have all these. The only one that seems reasonable is this root test. And then we went through. So I choose my test that would be best. And then we have to also select, right? Select all that apply. Answer the question, does the series converge or diverge? We saw that our limit from the root test was less than 1, so the series will converge. And great. So again, they explain the ratio test, they explain the root test, the integral test, the alternating series test, but definitely the root test. See, they mentioned the power of n here, right? So root test probably be best. Here's another one where the root test, now they're actually specifically asking us though to use the root test. Determine absolute convergence, and therefore convergence, of a series using the root test. So I'll do it once again. All right. Yeah, this one's actually very similar to the last one we saw. All right, so we got this series. The terms look like this. 4n cubed minus 5 divided by 9n to the 5th plus 5. But all this is raised to the nth power. Pardon me. So this is my a sub n. Now here, because this minus 5, not all the terms would be positive. You know, when n equals 1, you'd have negative 1 up top, 14 down here to the first. So negative 1/14 will be the first term. But after a while, as n gets larger and larger, these are all going to end up being eventually all positive. But still, we'll need the absolute value here just because of this whole possibility that terms could be negative. But anyway, I see this nth power on here, or some power involving n for my terms. So that'll indicate to me that, perhaps the root test is best. Now, they told me to use the root test, so it's pretty easy. Right? They told me what to do. Right? So let's do it. Right? So take this limit. Again, we're taking the limit as n approaches infinity of the nth root of the absolute value of our terms. Right? So this would be the limit as n approaches infinity of the nth root of the absolute value of these terms here, 4n cubed minus 5 over 9n to the 5th plus 5, to the nth. And once again, the nth root of something to the nth power, those are just like do each other. And this will simply be, the limit as n approaches infinity of the absolute value of, 4n cubed minus 5 divided by 9n to the 5th plus 5. And like I said, after a while, when n is larger and larger and larger, you really don't need the absolute values around this eventually, because these will all eventually be positive. And once again, we have a rational expression where the numerator degree is 3 and the denominator degree is 5, right? So this is going to 0 again, right? The denominator degree is larger. So just like last example, right? This limit as n goes to infinity of the nth root of the absolute value of our terms less than 1. So by this root test, the series is absolutely convergent, right? So therefore convergent. But they'll say absolutely convergent here. It is a test for absolute convergence. So the series converges absolutely. Submit. All right, great. So another root test. Notice again the terms here to the nth power, right? Some nth power on the term. So good indication that the root test would be best to determine if the series converges or diverges. So I'll write it out again. Sum from n equals 1. I'm gonna leave some feedback. 13n. Sorry about that noise. 13n over the natural log of n, to the nth power. This series should not start at 1, as the natural log of 1 is 0. Right, you'd have divided by 0. So I'm going to have n equals 2, unless they purposely did that. They'll have you be like, oh, this series can't converge because you have a division by 0. This is undefined, the value of this series. Don't think they meant that though, so I'm going to leave some feedback for them about this. Anyway, so here's a sub n, and I see this, nth power again on my terms. So it's a good indicator that the root test will be best for determining convergence or divergence of this series. So I take the limit as n approaches infinity of the nth root of the absolute value of our terms, which 2 onward, these would all be positive. So I really don't need the, the absolute value here. So this will be the limit as n approaches infinity of, now this would be the nth root of this expression to the nth power. So I'd be left with just 13n over the natural log of n, which is infinity over infinity. But if you applied L'Hopital's rule here, you'd see this was infinite. Polynomials are much larger eventually than logs. So the numerator would be getting a lot larger than the denominator would be. So this limit is infinite. Right, this limit ends up being infinite, which is definitely greater than 1. And you might so go back to my statement of the root test earlier. When this limit is greater than 1, the series will diverge. So back here, series diverges by the root test. Right. So you see this one with the factorial? See, there's a factorial and exclamation point involved. I would say that now, yeah, there's an nth power as well, but fa factorials grow faster than exponentials. We recall this from Calc 1. Factorials grow faster than exponentials. So so the factorial kind of outdoes this nth power down here. So when I see factorials, my gut goes to the ratio test. Right. I'll give that little tip to you. When I see factorials in my terms and I'm testing for convergence or divergence, I'm going to start with the ratio test. I'll write that up on my paper. But they are asking us, this is determine the absolute convergence of a series using the ratio test. And I'll bring that back when we need it. I wrote that on the paper earlier. So here we're given this, sum from n equals 1 to infinity of n factorial divided by 9 to the nth times n. Now again, if the whole thing was raised to the nth power, like the past couple examples, I'd use the root test. But not the entire expression's raised to the nth power, just this 9 down here. So yeah, the factorial is what's catching my eye. So I'm seeing factorial. I'm going to say up, try the ratio test. Ratio test. Again, if the whole thing were raised to the nth power, I would do the root test. So remember what the ratio test was. Got that back up here. I just maybe pause it, read through this again. But, these terms, n factorial over 9 to the n times n, that's my a sub n. And we're going to apply the ratio test to see if this series is absolutely convergent, right? And again, if it's absolutely convergent, then it's convergent. We find the following limit, right? The limit as n approaches infinity of the absolute value, right? It's a test for absolute convergence of, the n plus first term divided by the term before it, right? Divided by the nth term. Now, all these terms up here are going to be positive, so I really don't need the absolute value this time, but I'll stick to writing it. Keeping it on isn't really going to affect anything. So this will be the limit as n approaches infinity of the absolute value of, now, a sub n plus 1. That's just the terms of our sequence, the terms of our series here, where I replace n with n plus 1. So instead of n factorial, n plus 1 factorial. And instead of, 9 to the nth down here, you have 9 to the n plus 1 multiplied by, and then instead of n, you have the quantity n plus 1. All right, so that's a sub n plus 1. Then dividing by a sub n is dividing by this, right? The way it looks. Now, instead of writing divided by a fraction, dividing by a fraction, dividing by a sub n is the same thing as multiplying by the reciprocal of the a sub n. So dividing by this is multiplying by the reciprocal of this. So we have times 9 to the n over n, times n over n factorial. Close the absolute values. All right, so I got a lot of simplification going on here. Remember, n plus 1 factorial is n plus 1, and then times n factorial. And then same thing for, well, let me just get So you can see the n factorial up here, n factorial down here. And then there's n plus 1 up here, n plus 1 down here. A lot of cancellation going on. So this is all gone. That's gone, that's gone. I still have this n. That didn't go anywhere. And then 9 to the nth divided by, 9 to the nth plus 1, that's the same thing as 9 to the nth times 9. And so 9 to the nth will go away as well. All right, so here's what I'm left with. The limit as n approaches infinity of the absolute value of, n over 9. Which is definitely an infinite limit. All right, so this is approaching infinity, which would imply that the terms of our series, the terms aren't even going to 0. And I said it earlier, right? Factorials grow faster than exponentials. So this numerator would be getting much, much larger than the denominator will be. So the terms aren't even going to 0. So we could have also applied the divergence test. But we got this infinite limit here, right? The limit of this ratio. Pardon me, is infinite, which is definitely greater than 1. So remember, if this limit of this ratio of the n plus first term to the nth term is greater than 1, then by the ratio test, the series we're looking at diverges. So series diverges according to the ratio test. Great. All right. So again, now there aren't factorials, but I'm not seeing everything to the nth power either. And I would highly recommend using the ratio test over the root test if you can. Right. The only time I'm really going to advocate for the root test is if the entire expression is raised to some power, some nth power. But still, we're told to use the ratio test here. All right, so let me write this series up. Now this time, you got a polynomial in the numerator of each term and an exponential in the denominator. Polynomials grow slowly compared to exponentials, so these terms are going to 0. So this might converge. But again, if the terms are going to 0, it also might diverge. We don't know. That's why we're doing the test. All right. So we're given this sum, 1 to infinity of, and then n to the 6th divided by 5 to the nth. Right, so here's the a sub n, right, these terms that we're adding up. And I'm asked to apply the ratio test again. Right, so I'll write out once again the limit that you're taking here. The limit as n approaches infinity of the absolute value of the n plus first term divided by the previous term, right? Every term divided by its previous one. N plus first term divided by the nth term. Right, so this would be the limit as n goes to infinity of the absolute value. So first I replace all the n's in here with the quantity n plus 1. So that'd be n plus 1 to the 6th divided by 5 to the n plus 1. And then just like the last example, instead of dividing by a sub n, instead of dividing by this fraction, I'm going to multiply by the reciprocal. So times the reciprocal of these, which would be 5 to the n in the numerator now, divided by n to the 6th in the denominator. Well, 5 to the n plus 1 is 5 to the nth times 5. So I'm seeing 5 to the nth canceling here, and the absolute value of 1/5 is just 1/5, and that would be a constant multiple, which I can pull out of the limit. The property of limits, you can pull constant multiples out. So this is going to be 1/5 times the limit as n approaches infinity of the absolute value of n plus 1 to the 6th over n to the 6th, right? None of those cancel. But this is a 6-degree polynomial. This is a 6-degree polynomial. The lead term up here would be n to the 6th. The lead term down here would be n to the 6th. This is going to 1. So you have 1/5 times this whole thing's approaching 1. So the limit here is 1/5. 1/5 times 1. All right, so the limit of these ratios is 1/5, which is less than 1. Again, I wrote this up before, or showed you before. If this limit is less than 1, the series is absolutely convergent. Now therefore convergent. The series converges by this ratio test. What it converges to, I don't know. Right? We'd have to go to a calculator or something and figure out how many, to certain number of decimal places what this would converge to. That's not what the test is telling us, right? Tests don't tell us what the thing converges to. They're telling us the series converges. And, converges absolutely by the ratio test. Great. I mean, actually multiply the whole thing out. I wouldn't be doing all that. Okay. Here we're asked to use the root test to determine if the series below converges or diverges, right? Converges absolutely, which again would imply convergence, or diverges. Well, they don't give us sum here. It's notice the dot, 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 the ellipsis at the end. It's an infinite series. They don't give it to us in sigma notation, but I could very easily write it in sigma notation. Hopefully you see the pattern from one term to the next. So I'll write this out. So here's the series we're given. The first term of the series is 6 times 1 plus 6 divided by, and then 6 times 1 plus 5, all to the 1 power. Plus, the next term of the sum is, 6 times 2 plus 6 divided by, and then 6 times 2 plus 5, all to the 2 or plus, and then I'll just do one more. I know they have 4 of them there, but 6 times 3 plus 6 divided by 6 times 3 plus 5, all to the 3 power, right? So look at the value that keeps increasing by 1. It's this value here, right? These keep increasing. The rest of it doesn't change at all. You have the 6 and then the plus 6, 6, and the plus 5, and all these terms. So if I write this in summation notation, I'll have, I'll start from n equals 1. It's at 1 here. All these numbers are 1, then they're 2, then they're 3. Well, from 1 to infinity of, and then every single one of these terms looks like this. 6 times n plus 6 divided by 6 times n plus 5 raised to the n power. So there's a sub n, right? These 6 times n plus 6 over 6 times n plus 5 raised to the nth power. Notice, once again, it is all something to a power of n, right? To some nth power. Good indicator that the root test will be a good test. So once again, I'm applying the root test. So remember, you're taking this limit. The limit as n approaches infinity of the nth root of the absolute value of our terms, which, these are all positive. I don't really need the absolute value around this, but hopefully you can see that this would be this limit. All right, the nth root of, our terms are this to the nth power. The nth root and nth power will go away, and you're just left with 6n plus 6 over 6n plus 5. You can put absolute values around that, but these are positive anyway. And this is 1. And you just got like 6n over 6n, basically. This limit is 1. And, uh-oh, right? Remember, if this limit, same as with the ratio test, right? When you're doing the limit of those ratios, if this limit is 1, the test is inconclusive. You cannot tell if the series is going to converge or diverge. You'd have to figure out some other way to show it. But that's all we're asked to do, though, here. Use the root test, and that limit was 1. So the root test is inconclusive. All right. Okay, so unfortunately we can't say anything about the convergence or divergence of that series. I'd have to maybe go to a calculator and look at some tables and, perhaps do some sort of other comparison test or something else to try to figure it out. All right. And see this power. Now it's not to the nth power, but it is an expression, to a power involving n. The terms that we're adding up here look like 1 minus 7 over n to the, n squared power. So, power everything to some variable power, indicating that the root test might be a good idea. And use the root test to determine if the series below converges or diverges. So once again, I'll write the series out. I'll take that limit, try to apply the root test. So 1 minus 7 over n to the n squared power. So again, this is a sub n. These are my a sub n's that we're adding up. And this is to apply the root test. So same as before. This is the limit as n approaches infinity. Now, remember the nth root of the absolute value of our terms as some of these terms will be negative. So we need the absolute value here. Now, yeah, we need the absolute value. Now this is this limit. Limit as n approaches infinity of the absolute value of 1 minus 7 over n. Now I'll just put to the n squared outside this, right? Because there's properties of absolute value products, And then we're doing the nth root. Now, I'm going to rewrite this, okay? Remember the nth root is the same as raising, to the 1 over n power. That's the nth root. And then here I got power to a power. I can multiply these. So this is the limit as n goes to infinity of, 1 minus 7 over n to the nth power. Now, 1 minus 7 over n, which is the same as 1 plus, negative 7 over n to the nth power if I divide by -7 and multiply by -7 here, as n goes to infinity, you may recall something like this. This, right, this 1 plus something raised to the reciprocal of that thing would go to e. So this would be approaching e to the -7th. Right, this limit is e to the -7th, or 1 over e to the 7th, which is definitely less than 1. Right. So because this limit, ends up being less than 1, our series is absolutely convergent or convergent, right? Again, absolute convergence means, you make all the terms positive and then that converges. And if that's happening, then even the original series with the negative terms in it, some negatives in it would also converge. So the series is absolutely convergent by the root test. And again, that limit should have been e to the -7th, right? 1 over e to the 7th. Right, great. All right, so now back to see the factorial showing up again, right? They're telling us to use the ratio test. That's usually a good indicator if you see. Now, again, it doesn't mean you have to see factorials, right? We saw a problem earlier where there weren't factorials and we still use the ratio test. You can use these tests anytime you want. Really. I'm just giving you some tips, as to when would it be a good idea to use these tests. So when I see factorials, and it's not all raised to some power, right? This is not all raised to some power involving n. That'll be like, hey, let me use the ratio test over the root test. So once again, I'm asked to use the ratio test. Honestly, though, okay, I'm going to use the ratio test. You don't need the ratio test, though, to say that this converges or diverges. Anyway, let's just do it. So sum from n equals 1 to infinity. And the terms we're adding look like this. You got n factorial in the numerator divided by 5 times, and then n plus 1 factorial in the denominator. This can be simplified, though. N equals 1 to infinity. Because remember, n plus 1 factorial is n plus 1 times n factorial. So the n factorials can go away, and I'm left with this 1 over, and then 5 times n plus 1, which would be 5n plus 5. And you can probably already tell, I could do a limit comparison to just 1 over n and see that this was divergent. But let's call this, this is the same as this. So let's call this a sub n. They are asking me to use the ratio test. So remember that's find this limit. Limit as n approaches infinity of the following ratio, right? The ratio of the n plus first term to the nth term. So that's the limit as n approaches infinity of the n plus first term. I replace n with n plus 1, distribute the 5, that'd be 5n plus 5. This would be 1 over 5n plus 10. That would be the n plus first term. And then divide by a sub n. Divide by this, which is multiplying by the reciprocal of this, 5n plus 5, over 1. And what I have here is 5n plus 5 over 5n plus 10. This limit's 1. The lead term of 5n. So yeah, so here, the ratio test, this limit is 1. The ratio test doesn't tell us anything. say it's inconclusive. The ratio test doesn't tell us anything. So I'd have to go back and I remember I said earlier, looking at this, we could do a limit comparison or even direct comparison to 1 over n. So I would do limit comparison though, and see that this is actually a divergent series. The ratio test doesn't tell us anything. So we'd have to go and do a limit comparison or some integral test or something, right? Some other test. But if I'm using just straight up the ratio test, this test is inconclusive. All right, so be careful. Yeah, you might see that it's divergent, but the ratio test didn't tell you that. All right, so here I have another one where they're asking me to use the ratio test, which again, I think would be silly here. You see how this is very similar to some p series, right? You have 1 over 7 times, into the 9/5 in the denominator. This would add, 1/7 is less than 1. This is smaller. These terms are smaller than, just 1 over n to the 9/5. And if you were to add up the terms of 1 over n to the 9/5, that'd be a convergent p series. And if the larger ones converge, the smaller ones converge as well. This would be convergent by a direct comparison to a nice p series. You could also do a limit comparison to 1 over n to the 9/5 and see that this is convergent. But we're not asked to do that. We are asked to use the ratio test to see if we can determine if the series converges or diverges. Right? All right, so back here, writing the series again. So sum from n equals 1 to infinity of this, 1 over 7 times n to the 9/5 power. Here's a sub n. And we are asked to use the ratio test. So that's this, right? Take the limit as n goes to infinity of the absolute value of the ratio of, every term to the term before it, right? A sub n plus 1 to a sub n. So that's the limit. And then approaches infinity of the absolute value of, now just rewrite this with n plus 1 replacing n. So you have 1 over and then 7 times n plus 1 to the 9/5. But then times, the reciprocal of this divided by a sub n would be times the reciprocal of this, 7 times n to the 9/5 over 1. Just like the last example, can you see how this would be 1? It's basically like having 7 times n to the 9/5 over 7 times n to the 9/5, right? This little plus 1 here won't affect much when n gets large. So this limit is once again 1, which means the test is inconclusive. All right, so the ratio test again, for this example and the last example we saw, the ratio test doesn't tell us anything about whether or not the series converges or diverges. We would have to do a direct comparison or some limit comparison with a p-series. And you would see that this is convergent. The ratio test does not tell us that. It's inconclusive. So unfortunately, we've seen a couple of examples where that happens. Hopefully most of the series, you decide to do this with. And usually series involving factorials will be good for the ratio test to get some limits less than 1 or greater than 1, and you can tell right away if the series converges or diverges. And remember, if the series has terms with something to the everything to the nth power or some power involving n, the root test would be a good idea. But yeah, again, if those limits are 1 from the root test or ratio test, you got to try something else. Okay. So here's determine appropriate convergence test, right? So do I use the ratio test? Do I use the root test? Or just the divergence test, or limit comparison test, or regular direct comparison, or integral test, or alternating series test, whatever. Here we're asked to determine whether the series below is a geometric. All right, so this is like the very first example from the video. All they're asking us is if this is geometric or a p-series, or an alternating series, or none of those things. Now this one's a little trickier than the others, because they're hiding the fact that this is alternating in plain sight. All right, look at this sum. Sum from n equals 1 to infinity. You have the cosine of pi times n in the numerator, divided by 8n in the denominator. Well, look at this. Cosine of pi n. You know, you might recall from Pre-Calc 2 or trigonometry, whenever you took it, cosine of pi is -1. Cosine of 2 pi. Cosine of 1 pi is -1. Cosine of 2 pi, +1. Cosine of 3 pi is -1, and so on. This is just -1 to the nth in disguise. So instead of looking at that this way, you can look at it this way. And we have an alternating series. This will be alternating. All right, it would be a -1/8 plus +1/16 minus, so I'll write out the first few terms, -1/8, then +1/16, and -1/24, and +1/32, and blah, blah, blah. It's alternating for sure. So series is an alternating series. And again, they remind you about what a geometric series is going to look like, what a p-series is going to look like, alternating series. Okay. All right, so this one is like an example we saw earlier as well. It says determine which of the following tests would be best to use to determine the convergence of the series below. And then does the series converge or diverge? All right. Well, it is an alternating series. All right, you got this power of -1 here to the nth. But the terms that are alternating aren't going to 0. I mean, I guess because it's an alternating series, you could say alternating series test would be good, but really I'm seeing here the terms aren't going to 0. See the power up here, 3/8, that'd be 2156, and this would be 856. Right? 3/8 is bigger than 1/7. So like the numerator became much larger, much faster than the denominator, and then there'll be the terms aren't even going to 0. So right away, I mean that's honestly the first thing I always look at. When I'm given an infinite series and asked, does it diverge or converge? The first thing I look at is look at the terms, right? Look at the thing. Do the terms approach 0? Right? Is the limit of the term 0? Because if it's not, then it's divergent right away. You don't have to do any other kind of test. So I'm seeing that. I'd say the divergence test was best. And again, because the terms aren't going to 0, the series would diverge. I'm curious as to what they say. Yeah, so I the instructor cheat here. They're seeing the same thing I'm seeing. Again, that usually is the first thing I look for. Do the terms even go to zero? Because if they don't, it's divergent and you don't have to do anything else. Now, if they do go to zero, if the limit was zero, then I would apply the alternating series test. I would say the alternating series test was best. Then you could determine if it was convergent or not. Remember, comparison test, integral test, those were only for non-negative terms. This will have some negative term. Those were only for series with finitely many negative terms or no negative terms. This series would have infinitely many negative terms, right? So you couldn't apply the comparison test or the integral test to these unless you were looking at the absolute value, and then you could say if it was absolutely convergent or not, blah, 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 right? But again, the terms aren't going to zero. Divergence test tells me the series diverges. All right. And that looks like it's it. They remind you of what the divergence test is, the alternating series test. All right. Really, the alternating series only tells you when an alternating series converges. It's very specific. Comparison test, right? Integral test. Okay. Now they did the alternating series test, it looks like. But, you know, they see that the test fails, right? The divergence test would be best here. And the terms aren't, if you notice right away, the terms aren't going to zero, diverging. All right, so that looks like it for that assignment. Great. We saw the ratio test. And I would recommend use of the ratio test if terms are involving factorials in some way, and they can't be simplified to something without a factorial, right? We did see an example earlier where there were factorials, but the expression could be simplified to something without a factorial, and we could make an easy limit comparison or direct comparison in that case. So yeah, ratio test I would recommend using first. Well, first see if the terms are even going to zero. But the ratio test would be good with factorials. Then the root test we saw, right? That'll be good. I would recommend using that straight away. If you notice all the terms are raised to some nth power or power involving n, some power involving the index. And then of course they had that whole objective about, what's best to use. So when given a series, do the terms go to zero, right? I would try to see if I can figure that out by looking at it. Do the terms even go to zero? If not, divergent, right? Divergence test. Now, if they do go to zero, if it's clear that they do go to zero, then you got to think about it some other way. If you have a series of all non-negative terms, right, or finitely many negative terms, you could do a comparison test, limit comparison test. If those terms are eventually decreasing and you can match the terms with some continuous function, perhaps, the integral test would be good there. If it's an alternating series, right, you got that positive, negative going on, right? The power of -1. Try the alternate, and the terms. Well, this is the alternating series test, right? The terms that are alternating are, decreasing to zero. Then your alternating your alternating series will converge. And then, of course, I already mentioned, right? We got the ratio test, root test, right? Those are nice in certain situations, right? Factorials and powers and junk. Okay. So, as I said at the top of the video, questions I saw here may not be the same as the questions you see, but I'm hoping, that they're similar enough so that watching me do them here will help you when you work on them on your own. And thank you very much for watching.